Okay, I appreciate it's taken a long time to reach this point, but we've covered a lot of important fundamentals about vectors, vectors on slopes, a different perspective, and now we're going to figure out how to bust up a vector that's at an angle into its components. This is theta, so if this is theta, this side here is the opposite side, this side here is the adjacent side to theta. So we can figure out this component of how much the weight pulls down the hill based on geometry. This is, we can use, this is the opposite side, that's the hypotenuse side, so we can use sine theta is equal to opposite over hypotenuse. The opposite side is this unknown weight parallel to the slope. The hypotenuse is a known weight based on the mass of the piano, mg. And this theta, we know what the theta is. It's about 11 degrees in my problem. So I know w, so I'll multiply both sides by w. We know that weight, we know sine theta, so we can solve for the parallel, we can solve for the amount that the weight of the piano is pulling down the hill, and the man, so we know this, we can solve for this, and the man pushes against it. So while we can calculate that now, and the man pushes against it, so as much as this pushes down, he pushes up. And so there's the magnitude, right there, and the direction, he pushes in the positive direction. So it says the sign of the force should be entered correctly. It's going to be positive because the upward direction is going to be positive. All right. You know what? Don't worry about part B. Part B, can tell you right now, is the same as part A, except instead of the velocity being constant down the hill, so it should probably have been, I should have said 12 meters per second down the hill, it actually takes the same force to, once it's going up the hill, actually to push it up the hill. As long as you're not speeding, it takes more force to accelerate it, to start from zero and get it going, but actually once it's going, it takes no more force to keep it going up the hill than it does to let it down the hill without speeding up. It's kind of a trick question. We're going to get into work and energy later. It takes more energy to push it up the hill, but it doesn't take more force. You don't really, anyway, I don't like part B, you guys being asked that question now. I'll just tell you, part B is equal to part A. And the whole reason is velocity is still a constant. There's no acceleration, so the force must still be the same. But you don't really have to understand why yet. If the man pushes okay, we're going to have to do part C in another video. It's even harder.